This is a video on how to solve the 8 queens puzzle. We will be using tree searching to solve it. To better understand, you should know about tree searching first. If you don't, you should have a look at this video on tree searching. This is a problem often given in computer science courses. You have to put 8 queens on a chessboard so they cannot capture each other. Here's an example. This is the way the queen moves. Queens move in a straight line vertically, horizontally, and diagonally. They can move any number of squares in a straight line. What do we know? Well, you can put 1 queen per row, 1 queen per column, and no queen must be in the diagonal of any other queen. When we have 8 queens down, we have a solution. These are the basic things that we know. This is an interesting problem. There are over 4 billion ways to put the queens down on a chessboard. Only a subset fit those requirements. 4 billion is too much. We need to reduce this. We can look at it several ways. We know where the queen is. We know where she can go. We know which places she cannot go. Therefore, we know where the next queen could be. In this case here, there are 42 places where the next queen could be put down. The white squares here are where the next queen can go. We can pick any available place to try the second queen. There's going to be a maximum of 8 queens, so 8 levels. At 8, we have a solution. This should work. Generating all the possible places for the next queen is a little bit complicated. Programming for this could prove to be a little bit more difficult than expected. It is also difficult to prune for transpositions. Let's see if we can do better. We will generate a maximum of 8 new branches, 1 for each line. Like previously, we will have a solution when we have 8 queens down. We can put a queen at 8 different places on the first level, on the first row. The dark squares here is where we cannot put a queen down on the second row, on the second level. With the first queen in that position at level 1, we can put the next queen at level 2 on the second row at 6 different places. Then at 4 different places for the third row, and at 3 different places for the fourth row. The number of branches generated this way is far fewer. We quickly reach a dead end. At level 6, in those positions, we can't put any new queen down. Okay, let's backtrack. The X marks the place where we just tried. Next, we try the next possible square and meet a dead end again. We backtrack again, and this on and on. We should get the picture by now. This may not be the simplest method, but certainly beats picking new places at random. Let's give it a try. We know that given a number of queens positioned on the first rows on the board, the next queen cannot go on the same column, on the columns intercepting their right diagonal, and on the columns intercepting their left diagonal. And this is true for any number of queens. Here's an example. We have 3 queens on the board. The first one is on column 4, the second on column 1, and the third one on column 7. The first queen's diagonal intercepts the fourth line 3 levels up. The second queen 2 levels up, and the third queen 1 level up. So we can compute the columns like this. We know on which column they are, and we know on which column it will intercept. The first one is at column 4. 3 levels up, it will be 7. The second one is on column 1. 2 levels up will be column 3. And the third one, on column 7, will be 1 column up at column number 8. We do the same thing on the left. We subtract 3, 2, and 1 from the positions we have. So, if we were to write this in APL, given Q as the columns of the queens, we can find out that all the available columns are now the columns 1 through 8, except the ones where the queens are, except where the queens intercept on the right, and except where the queens intercept on the left. Here, a generate function for the queen, which is exactly what we said on line 1. So the 8 columns except where they are, except the right diagonal, and except the left diagonal. Furthermore, if we have 8 queens put down on the board, then we show them. The show queens program should take care of that. Here's an example of output. Try branch is our program that traverses the tree. We should have seen this in a previous video. It calls our generate function, and in this case here, it starts at branch 1 and 5. We have a queen on column 1 and a queen on column 5. And the rest is determined by these 2 positions. Okay, so let's have a look at this in APL. I'm using Dialog APL here, by the way. This is version 14. It should work in any APL except that this one is available here. So let's have a look at the try branch function. Here's the try branch function. As you can see, we give it a branch. Instead of the generate function, I have created a gen q8 function. Let's have a look at it. And the gen q8 function, basically, if you have found a solution, we call niceboard, and niceboard is a function that will just display the board nicely and returns no solutions. Otherwise, if we haven't found a solution, then we keep on looking for one, and we do exactly the same as we were doing before. We get all the 8 columns except the ones that we have found, except the left diagonal, and except the right diagonal. So once we've returned the new branches here, we try them each one in turn. So let's try that. So if we try to branch 1 and 5, we start at column 1 on the first row and column 5 on the second row. It works. And of course, if we were to try from the beginning, well, we could go on forever. There's 92 solutions here. So that's it. If you wish, I can send you the code. Just send me a message. Enjoy.